Now, in this part of the program, we'll look at two types of primary systems, delta systems and Y systems. We'll discuss the characteristics of each system and what they mean to transformer connections. A substation transformer supplies power to a distribution system. The way that the windings on the secondary side of the substation transformer are connected together determines if the primary system is a three-phase delta system or a three-phase Y system. We'll look at each of these systems, beginning with delta. Here we have a simplified illustration of three identical transformer windings. In a delta system, the ends of each winding are connected to the ends of the other two windings. When shown graphically, the windings form a triangular shape that resembles the Greek letter delta. In a three-phase delta system, each phase originates at a point where the ends of two separate windings connect. These points are 120 degrees apart and typically designated A, B, and C. Between points represents the phase-to-phase voltage of the delta primary system. In a Y system, the windings are connected differently. One end of each winding is connected together at a common point, which is called the system neutral. In most cases, the system neutral is grounded. The other ends of the windings are positioned 120 degrees apart from each other. When shown graphically, the connection resembles the letter Y. Traditionally, the ends of the windings are labeled A, B, and C. The system neutral is labeled N. Each phase of a three-phase Y primary system is formed by a connection between the end of a winding and neutral. In this example, connections between A and neutral, B and neutral, and C and neutral each represent a different phase of a three-phase system. The voltage value for each of the phases is the phase-to-neutral voltage of the primary system. These graphic representations of delta and Y systems are referred to as phasor diagrams. Phasor diagrams can be used to show a number of different relationships within a power system. For our purposes, we'll use phasor diagrams to demonstrate primary distribution systems and how transformers can be connected within those systems. We'll begin with a delta system. The delta primary system consists of three primary phase wires. On the delta phasor diagram, the primary phases are represented by points A, B, and C. In order to energize a transformer winding on a delta system, each end of the winding must be connected to a separate phase of the delta system. For the most part, the easiest way to identify a delta system in the field is to look at how a transformer is connected to the primary system. Notice that the H1 bushing on the left is connected through various protective devices to one of the primary phases. The H2 bushing on the right is connected in a similar manner to another phase. Provided that the primary winding of this transformer is rated for the phase-to-phase voltage of this primary delta system, it will function properly. Now, from this example, we can make some general statements about a delta primary system. First, a delta primary system consists of three individual phase wires. Second, transformers connected to a delta system will require connections to two of the three phases. Third, in order to make these connections, single-phase transformers used on delta systems require two primary bushings. In contrast to a delta system, a Y system is typically composed of three individual phase wires and a grounded system neutral. On the phasor diagram for a Y system, points A, B, and C represent connections to each of the phase wires. Point N represents the grounded neutral. Each primary winding in this example is energized by connections between the energized phase and the system neutral. In the field, a transformer connected to a Y system looks like this. In this example, the H1 bushing on this transformer is connected to an individual phase wire. The case ground on the side of the transformer is connected to the grounded system neutral. Provided that the primary winding of this transformer is rated for the phase to neutral voltage of this Y primary system, the transformer should function properly. Now, in some cases, you may also find two bushing transformers connected to Y primary systems. In order to do this, the primary winding of the transformer must be rated for the appropriate phase to neutral voltage of the system it's connected to. Here is an example of a two-bushing transformer connected to a Y primary system. In this example, the transformer is rated for the phase to neutral voltage of this Y system. The H1 bushing of the unit is connected through protective devices to a primary phase wire. The H2 bushing is connected to the grounded system neutral. From these examples, we can make some general statements about a Y primary system. First, the system will consist of three phase wires and a system neutral. Second, when single bushing transformers are used, the primary winding is energized by connecting it between an energized phase and the system neutral. Third, depending on the voltage rating of the primary winding, two bushing transformers may also be connected to Y systems. Now, keep in mind that regardless of the primary system a transformer is connected to, transformer windings only respond to voltage. Unless the rated voltage is applied to the primary winding, the transformer will not operate properly. Right now, read over the material in your text and answer the questions. If you have any questions about Y or delta systems, ask your instructor to help you. In this part of the program, we'll look at how single-phase transformers can be connected to provide single-phase service. And when we say single-phase service, we're referring to the type of service typically supplied to residential customers through connections to the secondary side of a single-phase transformer. In most cases, the service supplied to single-phase customers is rated at 120/240 volts. 120/240 volts is secondary distribution voltage that provides a customer with two voltage options. 120 volts, which is typically used to power electric lights and small appliances such as TV sets and radios, and 240 volts, which may be required to operate electric ranges and some electric dryers, heaters, air conditioning units, and other 240 volt equipment. In order to provide these two voltage options, the individual coils that make up the secondary winding of a single-phase transformer must be connected together in a certain way. We'll use this simplified illustration of the primary and secondary windings in a single-phase transformer to demonstrate the internal connections that we shall refer to as conventional transformer wiring. Now, here's the primary winding of the unit. One end of the winding is connected to the H1 bushing on the transformer. In this example, the other end of the winding is connected to the H2 bushing on the transformer. Here are the two individual coils that make up the secondary winding of the transformer. In this example, there are three secondary bushings mounted on the unit. Inside the unit, an end of one of the secondary coils is connected to the X1 bushing. An end of the other secondary coil is connected to the X3 bushing. The remaining ends of both coils are joined together at the X2 bushing. In most cases, the X2 bushing is connected to ground. In this arrangement, the coils making up the secondary winding are in series. 120 volts can be supplied by connections to the X1 and X2 bushings, or by connections to the X2 and X3 bushings. In both cases, the ground on the X2 bushing splits the secondary winding into two equal coils, each capable of supplying 120 volts. The secondary winding can also supply 240 volts. This is accomplished by connections between the X1 and X3 bushings. With this in mind, we can begin to see what the secondary bus supplied by this single-phase transformer will look like. It'll consist of 3 wires. One wire, usually referred to as the neutral, is connected to ground and to the X2 bushing. The remaining wires, generally called hot legs, are connected through leads to the X1 and the X3 bushings. Connections between the grounded neutral and either one of the hot legs will each supply 120 volts. Connections between the 2 hot legs will supply 240 volts. Now, regardless of the type of system that the primary winding is connected to, the secondary connections that we've just seen are typical of most single-phase secondary connections that you'll encounter on the job. There are, however, a couple of things that you need to realize about this example. First, the polarity of the transformer used for our demonstration is additive. This means the secondary bushings are designated X3, X2, and X1 when read from left to right. If this unit had subtractive polarity, the ends of the windings connected to the X1 and X3 bushings would be swapped internally. The secondary bushings would then be designated X1, X2, and X3 when read from left to right. Provided that the transformer is rated for 120/240 volts, connections between either of the hot legs and neutral will still supply 120 volts, and connections between the 2 hot legs will provide 240 volts. For the most part, the polarity of a transformer is of little concern when making single-phase connections. We mention it here as a reminder that transformers can have different polarity. This difference will become more critical when we get to 3-phase connections. Another thing you should realize about the example that we demonstrated is that some transformers have 4 secondary bushings instead of 3. On transformers with 4 bushing arrangements, the ends of the 2 coils that make up the secondary winding are each connected internally to a separate secondary bushing. This design provides the flexibility of changing the wiring of the secondary winding without having to go inside the transformer to change connections. To connect the secondary winding of this transformer in a conventional manner, the X2 and X3 bushings, which are connected to the ends of separate coils, are joined together by a metal strap or jumper. Here's what it looks like in the field. With this jumper in place, the connection between the X2 and X3 bushings functions as a single bushing. This connection is grounded. The X1 and X4 bushings become the hot legs of the unit. The combination X2 and X3 bushing serves as the ground point between the 2 secondary coils. Connections to the X1 and X4 bushings will provide 240 volts. Connections between either the X1 or the X4 bushing and ground will provide 120 volts. Now, the 120/240 secondary voltage that we've been discussing can only be supplied if the rated primary voltage is applied to the primary winding of the unit. On this unit, for example, the voltage rating is 7620/13200 Y. As we said earlier, the first number indicates that the primary winding is rated and insulated for 7,620 volts. The second number, 13,200 Y, indicates that the transformer is designed to be used on a 13.2 kV Y system. When all connections are made and the unit is energized, 7,620 volts will be supplied to the primary winding. The voltage induced in the secondary winding will provide 240 volts to connections between the 2 hot legs, and 120 volts to connections between either one of the hot legs and the grounded neutral. In this example, the voltage rating of the unit and its single bushing design virtually dictated the type of primary system it was to be connected to and how the connections were to be made. This may not be the case for every transformer that you encounter on the job. For reasons of efficiency and economy, Transformer manufacturers often build transformers that are rated for use on more than one primary system. If your company uses these types of transformers, you'll need to know how the ratings are indicated on the nameplate and the primary systems that they can be used on. In this part of the program, we've looked at secondary connections that provide 120-240 volt single-phase service. For the remainder of this program, we'll look at three-phase connections. For now, read over the material in your text and answer the questions. In the last part of this program, we looked at how a single-phase transformer can be connected to provide 120-240 volt single-phase service to a customer. In many cases, commercial, industrial, and some residential customers also require three-phase power to run three-phase motors and other equipment. To meet these needs, single-phase transformers can be connected together to provide both three-phase power and single-phase service. In this part of the program, we'll look at the primary connections for a three-phase transformer bank. The connections we'll demonstrate are three-phase delta connections and three-phase Y connections. In order to connect single-phase units together and have them operate properly, several conditions must be met before any connections can be made. First, since a three-phase bank must be connected to the same primary distribution system, the voltage ratings of each unit must be identical and compatible with the system they'll be connected to. If this is not the case, the proper voltage will not be supplied to the secondary load. Second, the kVA rating or capacity of each unit and the percent impedance of each unit should be similar. Otherwise, the unit with the lowest percent impedance and capacity will tend to take on more than its share of the load. This can result in inefficient operation, overheating, premature failure, and outages. Finally, if the units being connected together have dual voltage switches or other tap changing mechanisms included in their design, the tap positions on the units must be identical. If this is not the case, the proper voltage will not be supplied to the secondary load. Now, you may find that your company has other conditions that must be met in order to connect units together on your systems. Before building a bank, make sure that you know and follow your company's specifications for connecting transformers together. Now, assuming that all of these conditions have been met, there are two types of connections commonly used to build a three-phase bank: delta connections and Y connections. Let's begin with three-phase delta primary connections. As we've indicated, in a three-phase delta primary system, the ends of each winding in the system are connected to the ends of the other windings in the system. When connecting single-phase units together to form a delta-connected three-phase bank, the windings must be connected in a similar manner. That is, the ends of the primary windings of each unit must be connected to the ends of the primary windings in the other two units. Now let's see how this is done using this simplified illustration. Here we have three single-phase two-bushing transformers. To make our explanation easier to follow, we'll designate the transformers and their windings 1, 2, and 3. Each side of this phasor diagram represents a primary winding. As a reference, we've labeled the windings that correspond to the transformers 1, 2, and 3. Let's start with winding number 1. This end of the winding on the phasor diagram corresponds to the end of the winding connected to the H1 bushing of transformer 1. For the moment, we'll leave this end and go on to the connection at the H2 bushing of transformer 1. On the diagram, the H2 end of winding number 1 is connected to the H1 end of winding number 2. To make this connection on the transformer bank, we'll connect the H2 bushing on transformer number 1 to the H1 bushing of transformer number 2 using a jumper. On the phasor diagram, winding number 2 is connected at the H2 end to winding number 3. To make this connection on the transformer bank, we'll use another jumper to connect the H2 bushing of transformer number 2 to the H1 bushing of transformer number 3. Finally, on the phasor diagram, the H2 end of winding number 3 is connected to the H1 end of winding number 1. On the transformer bank, this is done by using a jumper to connect the H2 bushing of transformer number 3 to the H1 bushing of transformer number 1. The delta connection of the primary windings of the 3 transformers is now complete. Each end of a primary winding is connected to the ends of the other 2 windings in the same relationship as shown on the delta phasor diagram. To energize the primary windings in this delta-connected 3-phase bank, the bank must be connected to a primary distribution system. As we said earlier, your company will have specific procedures for connecting transformer banks to your systems. For illustration purposes, we'll look at one example of how this bank can be connected to a delta system. Here are the 3-phase wires that make up the delta primary system. In order to energize this 3-phase bank, each point where 2 windings are joined together must be connected to a separate phase wire. Let's start with transformer number 1. The H1 bushing of transformer number 1 is connected to the H2 bushing of transformer number 3. We'll connect a lead from the H1 bushing to one of the phase wires. Moving on to the connection between windings number 1 and number 2, we'll use a lead from the H1 bushing to make a connection to another phase wire. Connections to the 3rd phase wire on this system are made at the point where transformer windings number 2 and number 3 are joined together. Here's what a primary delta connection looks like in the field. Here's transformer number 1, here's number 2, and here's number 3. The primary winding in transformer number 1 is connected to the primary winding in transformer number 2 by this jumper. The winding in transformer number 2 is connected to the winding in transformer number 3 by this jumper. The delta connection is completed by this jumper, which connects the primary winding in transformer number 3 to the winding in transformer number 1. A lead from the H1 bushing on each transformer is connected to a separate phase of the primary distribution system. In this case, the connections are made through fused cutouts. Let's go on and look at a 3-phase Y primary connection. As the Y phasor diagram illustrates, one end of each winding is tied together at a system neutral that's grounded. The other ends of the windings are connected to individual phases of the 3-phase Y primary system. Now let's see how this connection is made using this simplified illustration of 3 single bushing transformers. For the sake of simplifying our explanation, we'll again number the transformers and their windings 1, 2, and 3. We'll also label the corresponding windings illustrated by the Y phasor diagram 1, 2, and 3. The neutral connection between the ends of the windings is made at the case ground on single bushing transformers. If properly rated 2 bushing transformers are used, the connection is generally made at the H2 bushings. Wire jumpers are used to tie the ends of the primary windings connected to the case ground together. In many cases, this connection is referred to as a Y-tie. When the Y-tie is made, it is connected to the grounded system neutral using a jumper. Once the Y-tie, or neutral connection between the windings, is made, all that's left to complete the Y connection is to connect the H1 bushing on each transformer to a separate phase of the Y primary system. Starting at transformer number 1, we connected the H1 end of its winding to a phase wire of the system. The same is true for transformer number 2. A connection is made from the H1 bushing to another phase wire. And the same is true of transformer number 3. The H1 bushing is connected to the remaining phase wire. Now here's what this connection looks like in the field. Here's transformer number 1, here's number 2, and here's number 3. The Y connection between the case grounds of all three units is made here. Notice that the case grounds are all connected together and then connected to this ground wire running to the system neutral. The H1 bushing of transformer number 1 is connected to a single phase of the system through a fused cutout. The H1 bushing on transformer number 2 is connected to a separate phase wire, also through a fused cutout. Finally, the H1 bushing on transformer number 3 is connected to the remaining phase wire through a fused cutout. With this connection, one end of each primary winding is connected to a separate phase wire of the three-phase Y primary system. The other ends of the primary windings are connected together using a Y tie and grounded. As we've said, provided that the voltage rating of the primary winding of each transformer is compatible with the primary distribution system, two bushing transformers can also be used to form a Y connection. The only difference is that the Y tie is made at the H2 bushings instead of the case grounds. The primary connections to the phases remain unchanged. In this part of the program, we've laid the groundwork for the majority of transformer connections you'll encounter on the job. Review this material in your text and answer the questions. When we return, we'll look at a delta-delta connection.